Well, greetings everybody. I would like to show you this question from my math lab about position, velocity, acceleration, motion, and calculus. I think before I begin the problem, I at least feel more comfortable giving you some background information. So I have this note page here to go over that. Here are the concepts that are involved. We'll start with this function. We'll say s is a function of t. And these are the variables we'll normally use. S gives the position of some moving object, and t gives time. Units will be specified in general, but it gives me the position at any moment in time. Okay, so that's the position function. Now this is two-dimensional motion. So the motion will be left and right, or up and down, or any two-dimensional axis. It doesn't have to be vertical or horizontal. It can be in any orientation, but there'll just be two directions. Okay. Now, whenever we define our axis of motion, we have to say like, well, where are the positive numbers and where are the negative numbers? Okay, it doesn't have to be that the positive numbers are right of 0 and the negatives are left. We can define it, our coordinate system, any way we want, but it must be specified. Okay, like this axis here is not horizontal or vertical, and I could say, well, look, there's where my 0 mark is. That's position 0, and I'm going to put the negatives over here and the positives over there. If I want to, I can do that. It just has to be specified somehow. So you might read the fine print. I noticed this one here says weight S is measured in feet, and the positive positions are going to be right of the origin. So no assumptions are made. You're told what that's going to be. Okay, now the derivative of the position function, whether you call it ds over dt with Leibniz notation or f prime t, gives you velocity. How we might understand that is some quantity of both direction of motion and speed of motion. So it tells you how fast you're going, and it tells you which way you're going. If that derivative is positive, motion is towards the positive numbers. The velocity doesn't tell you where you are, it just tells you where you're going and how fast you're moving. If the derivative was negative, motion would be towards the negative numbers, like however it is, So like if I got this coordinate system and the derivative is negative, I'm going that way, like wherever I am, okay? Or if I've got this coordinate system for two-dimensional motion and the derivative was positive, I'm going this way towards the positive numbers, okay? That's how we can understand that derivative. That's what it tells us, okay? Now, if you took the absolute value of the velocity, you would get speed. It would remove all the information about the direction of motion. So if velocity tells you the direction you're going and it tells you how fast you're going, and with absolute value you take the direction out of it, then it just tells you speed. It just tells you how fast you're going. Okay? If that is 0, the object's not moving. Okay? All right. If you take the second derivative of the position function with Leibniz notation or function notation, then that gives you acceleration. Okay? Acceleration tells you how the velocity is changing. Velocity tells you how the position's changing. Okay? So we'll make this inference about it. If the acceleration's positive, then the velocity is getting more positive or increasing. Okay? And I meant to write if the acceleration is negative. I forgot to write the inequality, but if the acceleration is less than 0, the velocity is decreasing or getting more negative. All right, so that's like a quick rundown of all the concepts. Now let's do this question. It says, can you graph the position function? Now, I'm not too worried about the graphing because whether it should be or not. I mean, there's just so many ways that somebody could graph something. You may have a graphing calculator. You may use something online. You may plot some points and try to piece the graph together from there. So I'm not really, I don't think it's good to spend time in the video about that. I will talk more about the graph of the velocity and acceleration functions, but I'm going to skip part A, okay? Part B, find and graph the velocity function. So here goes. The velocity, well, what did we say that was? You're given a position function, You're given a function that tells you where you are at any moment in time, and if I take the derivative of that, I get the velocity, which tells me my velocity at any moment in time, my direction and speed at any moment in time. Okay? If you want to just call that v of t, then that's fine for velocity. Now, this would tell me if I'm moving left or right. It would tell me if I'm not moving or stationary, and so on. I noticed that it does ask me to ask when, or it asks me, when is the object stationary? When is it moving to the right? When is it moving to the left? As if it just wants us to show that we understand this breakdown. That it might not be moving, it might be going left or right towards the positives or negatives, and so on. So that's what it's asking. I'll start by doing it like this. I'll say, well, stationary, so not moving, that would mean the velocity is 0. So I'll set this equal to 0, and I solve it, and I get at moments 3 and 5 seconds, at those times, it's not moving. It's stationary. At just those instants, okay? Once you get just a hair past the 3-second mark, it's moving again, okay? Or 5, like once it, like any microscopic amount of time after 5, it's already moving again. It's just at these moments that it's not moving. Okay, so there you go. There would be my answer to when is it stationary. Now, as far as the graph goes, I do want to analyze the graph of the velocity function right here. And unfortunately, you can do that lots of different ways. I'm conflicted on what to show you. I'm not going to just plug it into a graphing calculator and show you the picture, because anybody could do that. I'll talk real quick about some ways that you can analyze the graph, like if you don't have it. So since I know when it's stationary, I can test some times outside of that. Like I know it's stationary at 3 and 5 seconds. Okay, and so I could just test some times in our interval outside of and in between 3 and 5 seconds. And then I can make these conclusions that, well, since, say if I put 0 into that, it gives me a velocity of 45 feet per second, meaning it's moving right. I can make the inference that it's moving right at all times less than 3 seconds. Why can I do that? Well, because I know when the velocity is 0, and we have this assumption that the velocity can't change from positive to negative or negative to positive without transitioning through 0. All that means is that for ordinary moving objects, in order for it to change direction, it has to come to a brief stop. Okay, so I can just test these 3 times outside of and in between my zeros, and then I can figure out, okay, well, it's positive less than 3, it hits 0 at 3, it's negative between 3 and 5, it hits 0 at 5, and then it's positive after 5. Okay, I can plot the graph that way. Even if I don't know the exact shape, I know it's positive, negative, positive. Another way you could do it is, all this velocity function is a parabola. It opens upward. You can find the vertex at 4 and negative 3 right there. It's another way you could do it. However you graph it, here's our conclusion. It asks me, when is the object stationary? When's it moving to the right? When's it moving to the left? Well, it's all right here in the picture. It's stationary at times 3 and 5 seconds. Okay, the velocity is positive from 0 to 3 and from 5 to 7. Okay, so what does positive velocity mean? It means you're moving towards the positive numbers, which is to the right in this case. So it's moving right on these intervals. These are intervals. These aren't ordered pairs. These are not points on that graph. If I write parentheses 5, 7 bracket, that means a time interval where t is more than 5, but also less than or equal to 7. Those are called intervals. When's it moving left? Well, whenever the velocity is negative, which is between 3 and 5 seconds. Okay? All right, so I don't say bracket 3, bracket 5, because at those times it's stationary. It's moving left more than 3 seconds, but less than 5. Okay, so those are my answers to part B. Okay, I won't do part C because it just seems so simple. It says determine the velocity and acceleration when t is 1. would just be a matter of plugging 1 into those. But let's talk about acceleration. What did we say acceleration was? Acceleration is the derivative of the velocity, or the second derivative of the position, however you want to see it. So if I know that my velocity is 3t squared minus 24t plus 45, if I took the derivative of that, I'll get my acceleration. So that is 6t minus 24. There's your acceleration. All right. Now, I can do whatever you want to know about the acceleration of this object, I can tell you through that formula. Okay? What the question asks me is this. Determine the acceleration of the object when its velocity is 0. Okay, so let's see. I know its velocity is 0 at t is 3 and 5. So I will take my acceleration and put 3 and 5 in. And at t equals 3, I get that the acceleration is negative 6 feet per second squared. Those are our units for acceleration. It's distance over time units to the second power. So at t is 3, acceleration is negative 6 feet per second squared, and at t is 5, acceleration is 6 feet per second squared. Okay? Real quick, why do we have these units? The first time people see units of acceleration, to have time to the second power seems a little weird. I'll talk about why that is. Why are the units like that? Well, so acceleration is change in velocity over change in time. How's velocity measured? Feet per second. In this case, how's time measured? Second. So it's like we're dividing fractions. Like, what's 1/3 divided by 2? 1 over 2 times 3. So what's feet per second divided by seconds? If you like treated those like numbers, they'd be feet over seconds squared. Okay. Now, so here's our acceleration function if you want it. I notice that this hits 0 at t equals 4, okay? Where your acceleration is 0 at that moment, the velocity is not changing. And we have positive acceleration for times more than 4, negative acceleration for times less than 4. And I do think it's important, like most people who take calculus, take physics also, to really understand motion and velocity and acceleration. So, like, is our velocity consistent, like up here? Is it really true that the acceleration is negative, or that the velocity seems to be getting smaller up to time t equals 4? I can see that because look, this is your velocity, which gets lower and lower and lower and lower and lower and lower until you get to 4, where it reaches its absolute lowest, and then it starts to get bigger. So I can see this information consistent with that. Okay, so let's do part 3, talking about the speed. Okay, it asked me about that. It says, oh, we'll determine the acceleration of the object when the velocity is 0. Okay, we did that. On what intervals is the speed increasing? Okay, so speed is the absolute value of the velocity. It just takes the velocity and removes information about the direction of motion, leaving only behind how fast the object's going. So speed would be this, the absolute value of 3t squared minus 24t plus 45. So, which seems like a kind of a strange thing to graph, but I know that it would just be our velocity function, just making all these numbers positive. It wouldn't affect this part of the graph or this part of the graph, but it would reflect this part of the graph across the horizontal axis, because these negative numbers would become positive. So it'll make it look something like that. Okay, so here's your speed. We slow down, we speed up, we slow back down, we speed back up. Okay, so if you would like to know, in addition to that, when is the speed increasing, over what time intervals is the speed increasing, then I see, well, right here, like wherever this curve is rising, basically, and so that's from time t equals 3 to t equals 4. Okay, that's this interval, leaving out the 3 and the 4. Okay, and from 5 to 7, this interval, leaving out the 5 but including the 7. Okay, all right, so those intervals, that's my answer to that last question. All right, well, what intervals is the speed increasing? Okay, so that's everything about this particular question. Okay, I think for whatever else you see about motion from position functions and derivatives and so on, other questions like that can be traced back down to this initial note sheet. The math might be more or less complicated than what you see here, but the origin in all those concepts, as you might apply them, is right here.